this lecture, we continue our discussion on the wave number approach. Last time, we had introduced the complex representation of a harmonic function, and we looked at the analytical form of its derivative, and then we derived the discrete form of the derivative using the CD2 scheme. And then we showed that the wave number that we see coming from the analytical derivative does not exactly get matched by the wave number expression that we get from the finite difference approximation using the CD2 scheme, and we use the nomenclature k dash for representing the so called modified wave number. So, just to recall, we will write the expression for the modified wave number once more for the CD2 scheme. So, we found last time that for the CD2 scheme, k dash is equal to sine of k times delta x by delta x. So, delta x of course, is our grid spacing and k is the wave number of say a sinusoidal wave that you are accommodating within your domain, which has a length of L, and we said that the waves could be coming in like this in integer form. That means, we have complete waves accommodated. So, these are some of the things we already discussed in the last lecture. So, today we work out another example. So, we have earlier derived the CD4 discretization for the first derivative using the Taylor table approach. So, let us discuss about the wave number approach with respect to the CD4 scheme. So, the target is that we try to work out the k dash for the CD4 scheme now, of course, for the first derivative for the f dash. So, we have already achieved that for the CD2 scheme, that how the k dash looks for f dash using central differencing of second order accuracy. So, we use the same methodology, but this time by using the CD4 discretization. So, we recall that the f dash expression for CD4, which we had already derived using the Taylor table approach, is given by this expression. So, now like we discussed earlier, we need to have representations for all these functional values at the different grid points. So, let us try to do that. So, we just recall this nomenclature which we discussed earlier, that here the I minus 2 is in the suffix, and you need to convert it to a length in terms of the grid spacing, and for that what you do essentially is multiply the grid spacing by the grid index corresponding to that point. In a similar manner, we define it for f I minus 1, and then we need an expression for f I plus 1 and f I plus 2. you have to be a little careful with the use of capital I and small I. So, just to recall, capital I stands for under root minus 1, I is the grid index. So, we need one more expression, that of f I plus 2. So, now we are ready with all the expressions for the functional values on the grid. So, we have a discrete domain. So, we need the functional values at the discrete grid points, and we have them all. Now, we would just substitute them in the expression for f dash. So, what we have here is, we could write it this way, where you take out the common factor. So, this e to the power of I k delta x I is common to all of those functions, and the rest of it could be put in the bracketed term. This would be plus 2 capital I k delta x, the whole divided by 12 delta x. That will be the expression. So, we need to now club the terms. So, these two terms will be clubbed together, and again these two terms will be clubbed together. You can figure out why, because you have similar looking indices here, and you have similar looking indices here for the starting and the end terms. So, let us do that exercise. Remember that this is a product, delta x into I is not a suffix here. So, this expression can be called as f I. So, what we have here is f I by 12 delta x, and then we can write 8 into 2 I sin k delta x. We have explained earlier why we get a 2 times sine with the capital I here. This comes from the Euler formula. Be careful to put in this 2 inside. So, this can be written as as you can see, we are gradually getting it arranged into a form which can be easily compared with the analytical form. So, you remember that f dash was equal to I k f. So, you can very well imagine that whatever comes out from here will actually become the k dash for us for the CD4 scheme. So, we continue in that direction. So, we can expand this term for example. So, this is like 2 sin 2 theta. So, that will give you 2 into 2 sin theta cos theta. So, that means once you do that, you can have a 4 coming out here, and then you already have a 16. That means 4 will come out as a common factor from the numerator. You also have a 4 into 3 from the denominator. So, the 4 cancel out whatever you extract as common factors from numerator and denominator. So, you have 4 sin k delta x left with the first term, and you have sin k delta x cos k delta x by 3 delta x times f I. So, we have arrived at the expression for k dash. So, what we have here is k dash for CD4 scheme, and of course, for the first derivative, and the expression turns out to be 4 sin. So, let us take sin common. We will put 4 minus cos k delta x times sin k delta x, the whole divided by 3 delta x. So, this is our expression for the modified wave number for first derivative using CD4 scheme. Modified wave number for first derivative using CD4 scheme, to be more precise, finite difference scheme. So, we achieved our goal of obtaining the modified wave number expression for CD4 scheme, and now we still do not know how far these k dash expressions are from the analytical k that we were talking about, and we certainly need to plot and see how well they are doing. The CD2 scheme and CD4 schemes are doing for different values of k, because we already realized that there is a provision for accommodating different values of k. That means, waves of different frequencies to span the domain L. And as you try to apply these finite difference schemes to approximate the derivatives, and when these derivatives are working on waves of different frequencies, how well are we doing using these approximations. So, we need to find out more by doing a few calculations using these k dash expressions. So, let us try to do that. So, just to go back to how we defined these parameters delta x and k. So, delta x was defined as L by n. L is the domain length, n is the number of intervals that you divided that domain into, that you divided the domain into. That of course depends on what delta x you are choosing. That means, the smaller the delta x, the larger would be n, and vice versa. And we remember that k by definition was 2 pi by lambda, and how did we obtain lambda? We said lambda is equal to that domain length divided by the number of wavelengths we are accommodating within that length. That means, this small n was the number of waves or wavelengths accommodated within the length L, and so this would become 2 pi n by L, and we know that n varies from 0 to capital N by 2. Again, you must be remembering that the shortest wave would take up a distance of 2 times delta x, and this factor 2 basically is connected with the fact that the shortest wave takes up 2 times the grid spacing. Now, the important thing to look at is what is this k delta x that we are seeing in the modified wave number expressions both for the CD 2 as well as the CD 4 scheme. You may be noticing that in both the formulae we are seeing this k times delta x coming up. So, what is this k times delta x? So, let us try to substitute those expressions and try to work out what this k times delta x is all about. So, we find that it is nothing but 2 pi small n by capital N, and again n is anything of course in terms of integers varying from 0 to n by 2. So, that will give me the maximum and minimum values of k times delta x, because that is basically the maximum and minimum values of small n. So, the minimum of k times delta x is 0, which corresponds to n equal to 0, and the maximum k times delta x is equal to 2 pi by n into n max, which is 2 pi by n into n by 2, and you get pi. So, the maximum value of k times delta x would be pi. So, we have to look at a range of k times delta x spanning between 0 to pi as we look at these expressions of k dash, and then see that for those values of k where these k dash values are. So, we can do a few simple hand calculations to do a quick check on this. So, let us try to do that. So, we form a kind of a table for our hand calculations, and let us take a few discrete values and try to check how the k dash values are doing for the two schemes. So, we will choose values of this kind. Remember that this k times delta x is in radians. So, when we operate the sine or cosine operator on the angle, so we know that we apply the expression in terms of radians. So, I choose radian values of the angles, say pi by 4, which essentially means 45 degrees is so here the k times delta x will have a value of 0.785. For pi by 2 it is 1.571. This is the degree value, and then 3 pi by 4 would have a value of 2.356. Of course, they are approximate values, correct to 3 places after decimal, and the last value will correspond to pi. So, this is 180 degrees. And then we try to find out what k dash times delta x is for the CD 2 scheme. So, it turns out to be k times the expression for k dash delta x is equal to sine k times k delta x for the CD 2 scheme, and the k dash delta x for the CD 4 scheme will be 4 minus cosine of k delta x the whole multiplied by sine k delta x divided by 3. Now, as you can understand that when k delta x is equal to 0, then this is going to yield a 0. Now, how about this? You will get a 4 minus 1 because cos 0 is 1, but then it gets multiplied with sin k delta x, which is 0. So, finally, you will get a 0 here. That means, you actually can match exactly between the analytical and the approximate forms here when k times delta x is 0. This again remember it corresponds to n equal to 0, which means you just have a constant value of the function. So, the derivative essentially is 0 and the finite differences are also turning out to be 0, which is consistent. When you go to pi by 4, this will give you a value of 1 by root 2, which is approximately 0.707. Here you will get a value of 4 minus cos pi by 4 into sin pi by 4, both of them being 1 by root 2 whole divided by 3, and that will give you a value of 0.776. So, you can figure out that this value is already falling short of the analytical value, which is 0.785, whereas this CD4 approximation is still fairly close till k times delta x equal to pi by 4. Now, let us look at pi by 2. So, at pi by 2, this will give you a value of 1, which is already quite low compared to 1.57. Now, as far as CD4 is concerned, you will get a 0 here, you will get a 1 here, and then the final value will be 1.33 approximately, which is falling short of 1.57, but still better than what CD2 is giving you. Then as you move on to the other angles, you can calculate the values like we did for the lower values of k delta x. And then finally, you find that both the schemes are showing up with a value of 0 when the actual value should have been 3.14. That means, in this range both of them have deviated far from the exact expression. Now, if we were to plot this exactly over the range of values of k, we would be able to see a graph which looks like this, and you find that in the lower ranges of k times delta x, you have a fairly good match, but then you can see that the red dotted line, which stands for CD2, is deviating off from the exact plot earlier than the blue plot, which stands for CD4. So, essentially CD4 is close to the exact values up to these ranges, and then the deviation is enlarging here, but you can see deviation starting for CD2 earlier. And of course, what we noticed was that at much higher values of k times delta x, both of them have deviated significantly. Now, what is the outcome of this analysis, or what are the conclusions that we can draw from an analysis of this kind? So, we can say that the modified wave number, which comes from a finite difference approximation, of which we tested 2 for first derivative, that compares well with the exact wave number at small values of k. However, for higher values of k, the finite difference schemes are having poor approximation. The question is that even if you go for still higher orders of formal accuracy, you may not still be able to achieve very good performance at higher wave numbers, but the motivation would be to push higher and higher, so that you get superior accuracy up to a fairly large value of k delta x before it droops down. So, can we have schemes which are having superior performance of this kind? We have seen that the higher formal accuracy schemes have performed more superiorly, because CD 4 has excelled over CD 2 in the modified wave number plot. And like we did for the first derivative, we can also do a similar exercise for second derivatives, because many of the fluid dynamics equations involve second order derivatives. So, we need to know how the schemes are doing on second order derivatives. So, we learned a more contemporary way of assessing accuracy of finite difference schemes, and in all these exercises that we did, we have shown that the expressions that have been derived are essentially explicit expressions. Explicit expressions of the derivative, which means that the finite difference approximation gives you a formula for calculating f dash at a grid point I in terms of functional values in the neighborhood. So, which may involve I minus 1, I plus 1 and other points. That means, you can get the expression for the f dash, the approximate expression for the f dash can give you the value at that grid point the moment you substitute for the functional values on the right hand side of the equation. So, that kind of a calculation is called as an explicit calculation. So, as long as you have the functional values, which we normally have, we can substitute on the right hand side of this equation, and immediately the difference expression helps us to calculate the f dash approximately at the grid point I. Now, there could be schemes where such explicit calculations are not done. Calculations of the derivatives are done by so called implicit means. So, let us have a quick look at the appearance of such schemes. So, we could be having implicit finite difference approximations. So, as we mentioned earlier, that the schemes that we have discussed till date, say CD 2, CD 4, or earlier we have discussed about first order accurate schemes involving forward and backward differences, all of them were explicit schemes, which we just discussed about what the explicit scheme essentially means. But if you look at a scheme like this, where the derivative at the grid point I, the derivative at the grid point I plus 1 and the derivative at the grid point I minus 1, all first derivatives are being simultaneously calculated here. Now, even if you substitute the functional values at these points, you cannot get a direct value of f I dash from this equation. This will not be possible, because there are more derivatives involved here in this equation. And of course, we do not know what is the formal accuracy of this approximation, but that is a question that we need to look at later. Right now, we are just trying to figure out that where this implicitness comes from. So, what we understood was that an implicit expression would mean that the derivative cannot be calculated at a grid point just by substituting the functional values which are involved in the finite difference approximation directly, but rather the derivatives have to be calculated at that grid point as well as the derivatives at some neighboring grid points in a simultaneous manner. And therefore, what you can understand is that there would be a system of linear algebraic equations which will come out in the process, and then you would need to solve the system of linear algebraic equations to obtain these derivatives at the different grid points simultaneously. So, once you solve for the system, all the derivatives will be worked out at a time, but they cannot be just worked out by substituting the functional values by using a single equation. So, this kind of a calculation is an implicit calculation. We will talk more about this implicit formulation in the next lecture. Thank you.